Is that playing? Oh yeah, it's going. So what is playing the role of r here? R is 2 minus 2x. R is the function. So the length of this red segment there, that's playing the role of the radius. So the distance from the x-axis up to this curve right there, that distance right there, is forming the radius of the corresponding disk. And that radius, so little r, we can put a little r right in there. That is the function. So for us, we're going to have pi multiplied by 2 minus 2x quantity squared. That's going to be the area of the disk at x. And if we FOIL this out, because we know we're going to need to integrate, if we're going to integrate, we'll have that. And if we wanted to, we could factor out a 4 to make the function a little bit simpler. Don't have to factor out the 4, but you can. Okay, so everybody with us for the area? So that formula up here, this is just the area of the disk. Pi times the radius squared, where the radius is given by the function. So pi r squared. And our volume then, they tell us that the limits of integration are going to be 0 to 1. We're integrating with respect to x-axis. So the integration element, or the vertical rectangle, is moving across x's. So you can imagine drawing all these vertical rectangles. They are with respect to x, right? For all the x's between 0 and 1, you should envision a rectangle or a vertical segment of some sort. So those are the integration limits then. So the volume will be the integral from 0 to 1 of the area function. So the 4 pi, which will be a constant that can factor to the front. So there is our volume formula. The 4 pi comes out, and then we do our integration technique for polynomials. We add 1 and divide by the new exponent. And we've got that. And then we evaluate our antiderivative by using the upper minus lower process. So if we plug in the upper limit of integration, we have 1 going into there gives 1/3 minus 1 plus 1. So that's the antiderivative evaluated at the upper limit of integration. And then we subtract off the antiderivative evaluated at the lower limit of integration, subtracting off 0. So we end up with 4 pi divided by 3 cubic units. That make sense? Now this is a geometric object that some of us probably know the volume formula for, because it's forming a cone. Do we know the volume of a cone? So if we have a cone like this, anyone know what the volume of a cone is? 1/3 pi r squared h, I believe. So pi r squared is the area of a disk, and then you multiply by the height, so that would be the area, or the volume, of a cylinder, and then you take 1/3 of that to get the volume of a cone. So the volume of the cone is going to be, so you can imagine it's sitting inside of a cylinder. It's going to be less than the volume of the cylinder. Pi r squared times height will give you the cylinder, and then 1/3. So let's check. So if we were looking at this, we'd have 1/3 pi r squared. So the radius here is going to be this dimension. It looks like it goes up to 2. Let's just double check. Yeah, 2. That's the So this cone, we're going around the x-axis, so that's going to be the radius of the cone, and the height of the cone is horizontal. So the radius of the cone is 2, so we'd have 2 squared. The height of the cone is 1, and we would get the same exact answer. You don't always know a geometric formula for the area of the solid that you're investigating. In this case, it happens to be a cone, so we could, if we know our cone formula. Let's try another one of these. So here is a region in the xy plane. It's touching the x-axis. So when it rotates around the x-axis, there's no holes or anything in the object. Every cross-section is going to be a disk. And here's a picture of the solid object with one cross-section or one slice. And with the solid kind of peeled away a little bit. So once again, when we draw our element, we're going to draw a vertical element at x. We're rotating around. And you can imagine that element right there, when it rotates around, it's creating that disk. All right? And the radius of this is right there. That's the radius of the disk. The radius of the disk is given by the function. That's what the function is going to measure. So that function, e to the negative x, is measuring the radius. So once again, we first want to come up with our generic formula for whatever the geometric cross-section will be. There's our generic formula. And then we look to the specifics and figure out, oh, well, what is the function doing? How do we get rid of r? We don't integrate with respect to r. So we are going to have pi, and then our function is measuring the radius, that's e to the negative x, quantity squared. So there is the area of the disk at x. If you plug in 0, you're going to get the area of this unit disk. If you plug in natural log of 4, you'll get the area of the disk over there at the end, the smallest disk. So how does this simplify? Pi times e to the negative 2x. Power to power, multiply. Not add, multiply, power to power. And then our volume is the integral across our interval. So here's our interval right there, 0 to natural log of 4. 0 to ln 4. We'll integrate this function. The pi comes to the front, and we're left integrating this, which if you were in Calc 1, what technique would you use? Substitution. But that is a linear function up here, so we've seen that when you're doing substitution, where you have a linear substitution, instead of using substitution, we can use reverse chain rule. Calc 1, you learn the chain rule for derivatives, and that is multiply by the derivative of the exponent in this case. For us, reverse chain rule means divide by the derivative of the exponent instead of multiply by it. So for an integral or a derivative of an exponential, the first step is itself. So the integral or derivative of an exponential is itself. So we rewrite it. If we were differentiating, we would multiply by negative 2, but we're integrating, so we divide by negative 2. And limits of integration. So I'm going to pull the constant out to the front here just to keep it a little cleaner. So I'm going to think of the antiderivative part as this right here. So there's the antiderivative part inside here. So this function gets evaluated at the upper limit of integration. It gets evaluated at the lower limit of integration, and then we subtract the two. And this one, when you plug in 0, you do not get 0. So upper limit is going to be e to the negative 2 natural log of 4. There's the upper limit evaluated. Now we subtract off the lower limit evaluated. So plug in 0 for that x, negative 2 times 0, 0. All right, now we have to do some algebra. We need some log properties here. Who can tell us what this thing simplifies to? What does that simplify to? Nope. E to the 0 will go to 1. E to the 0 will go to 1. But e to the negative 2 natural log of 4? Nope.
Is it 4 to the negative second power?
Which is?
Which is... hold on.
4 to the negative 2, which is? 1 over 4 squared, which is? 1/16. This will simplify to 1/16. 1/16, and then minus 1. So recall from algebra that negative 2 natural log of 4, log property says that coefficients can fly up and become exponents on the inside. Oh, why did I put the 4 up there? Right there. So this is going to be natural log of 4 to the negative 2. Where'd my e go? Oh, somehow I must have erased the e. So we have negative 2 natural log. Oh, it's e raised to that. There's the e. Sorry about that. Natural log of 4. So we have that. And then the superpower of coefficients with log functions, that's going to be 4 to the negative 2. And then e and natural log are inverse functions, so this simplifies to 4 to the negative 2, which is 1 over 4 squared, which is 1/16. And that tells us then that we have negative pi over 2, 1/16 minus 1, so that's negative 15/16. And our final answer will be positive 15 pi divided by 32. That'll be our volume. Yeah, Calc 2. You gotta reach back, blow out the cobwebs, all that algebra, all that trig. We use the algebra and the trig way more in Calc 2 than you do in Calc 1. So you gotta clear out the cobwebs. All right, we are down here somewhere. Let's slide that up. So let's take a look at the situation where our solid object is created with a rotation, a revolution, but where there's a gap between the region and the axis that you are rotating around. So if you have your region and it's not touching the x-axis when you rotate around the x-axis, there's a gap, you're going to end up with cross-sections that are, we call them washers. So if I look at the cross-section at x, when that red segment rotates around, there's that gap, so that's going to create a hole. So you're going to get a washer instead of a disk. And the area of a washer is the pi r outer squared minus pi r inner squared. So you're going to take the big disk and subtract off the little disk to get the area of the washer. Mathematically, this shape is called an annulus. In Calc 2, we just always refer to it as a washer. So the area of this annulus or this washer will be pi times the outer radius squared minus pi times the inner radius squared. And that's what the functions are representing up here. This first function is representing the outer radius, and the second function is representing the inner radius. So let's try one. So our cross sections are no longer disks, they are washers. So here we look at this region in the xy plane, let's draw a random element in there. Integration element, rectangle, whatever you want to think of it as. As it rotates around, it's going to create this cross-sectional washer. So this space right here between your region and the axis of rotation is creating the hole in there. Okay, so the area of a washer. So the area of a washer is where we're going to start. That's going to be our cross-sectional shape. We need to use geometry to find the area of that cross-sectional shape. So this is going to be pi times the outer radius squared minus pi times the inner radius squared. Bless you. So that's just big disk minus little disk to get the area of the red. Well, the outer radius is the one that's furthest away from the axis of rotation. So that distance right there is the outer radius. The inner radius is the one that's closer. So this distance right there is the inner radius. Oops. Looks a lot like an O. That's the inner radius. So the distance from the axis of rotation to the further function, that's the outer radius. The distance from the axis of rotation to the closer function is the inner radius. So let's see what we end up with. So we can factor out the pi here, of course. So outer radius is this function, the green one. So that's x to the 1/4. And then we're squaring that. Minus the inner radius, which is just x. And then we're squaring that also. So that is going to give us the area of the washer at x. If we simplify this a skosh, we'll have x to the 1/2, power to power we multiply. So there is our simplified area function. The volume will be the integral of this. And then we have to figure out our limits of integration. So volume, integrate area. Limits of integration. We need to know where the two curves intersect. How do we figure out where curves intersect? Yeah, we just set them equal to each other. So we have x raised to the 1/4 power. We want to set that equal to x raised to the 1st power, so we have that. That's certainly a nonlinear equation. So at some point we're going to shove everything to one side and factor. The best way for nonlinears usually. But we hate that fractional exponent. Is there something we can do to both sides to get rid of that fraction in the exponent position? We can raise both sides to the 4th power? If we raise both sides to the 4th power, that's going to get rid of that fractional exponent and make our lives way easier. So we'll get that. 4 times 1/4 is 1. Now everything to one side and factor. So we can subtract the x over, we can factor out the x. And this tells us by the zero product rule that we only have 2 solutions. Those curves can only intersect when x is 0 or x cubed is equal to 1. X cubed is only equal to 1 when x is 1. So those will be the limits of integration. And then we can do our typical power rule stuff. Add 1 to the exponents. We're going to add 2 over 2 to get 3 over 2. Divide by 3 over 2 means multiply by 2 over 3. And then x to the 3 divided by 3. evaluated on the interval 0 to 1. And then we use our fundamental theorem of calculus technique, plug in the upper limit, plug in the lower limit, take the difference. So we're going to have the pi out in front. Plugging in the 1 is going to give us 2/3 minus 1/3. And what do we get when we plug in 0? 0. So subtract off 0. So we get for the total volume pi divided by 3. Bless you. So quite frequently the math is not too hard. The integration is not generally the hard part. It's usually the concept. It's usually conceptualizing what's going on. Understanding that when this is rotated around, you get a washer, understanding the geometric formula for the area of a washer. That's usually the harder part, the setup. Any question on part of that? Any part of that? Yeah?
For the limits of integration, why'd you power it to 4?
So we need to solve this equation. And when you have a fractional exponent, like if you are clever, you could say, okay, this is going to be x minus x to the 4th equals 0. That's a harder equation to solve than this one. This one it's obvious, you can factor out the x and you get a product. This one, you do it similarly. You would factor out the x to the 1/4, but it's a little harder than raising each side to the 4th power. What would you get in here if you factored out x to the 1/4? You get a 1 there. What do you get when you factor x to the 1/4 out there? X to the 3/4. Because you have to add them to get to a power of 1. So then your 0 product rule would say x to the 4th equals 0, or x to the 3/4 equals 1. And those are just a little bit more kind of squirrely. Yes, the only way the 4th root of x is 0 is if x is 0. So that does give you x equals 0. And then here you would raise both sides to the 4/3 power, and 1 to the 4/3 is 1. So you will get the same answers, but it's easier if you have that type of equation to get rid of the fractional exponents first. Just a little less power on the brain if you can get rid of your fractional exponent. A little less brain power. All right, you ready to try one? You look amped. All right, go for it. Find the volume of this shape. I don't know what you call that shape. Find the volume of that solid of revolution. It's got a cone drilled out of it. So we're rotating that region R around the x-axis. There's a picture of a portion of the solid with one of its cross sections or slices. The cross sections will be washers. So try to identify the outer radius, the inner radius. You know if you're freaking out and need a nudge. Oh, yeah. Oh, good. Oh, good. Yeah, if you ever need to get up and walk around, feel free. It's totally fine. If you want to stretch your legs and stand in the back against the wall for a moment, no problem. I'm just going to draw the element up here, the integration element. That little red segment's rotating around the x-axis, creating an annulus, aka a washer. That just seems way too simple. Well, it could be right. Yeah, that x squared, yeah, and then they get that. Yeah. Looks very plausible.
We did this in Calc AB, so it's the wall.
Oh,
this is
you
your area
did.
function of the wall.
But you didn't do shells in AB, which
That sounds a little scary.
which is crazy that they give you full Calculus 1 credit when they don't even, or Calc 2 credit when they don't
We don't need to
cover.
find the
Wait, you did that in
bounds,
AB,
really,
not
just
BC, yeah, AB.
give it to
AB.
us.
Yeah.
Yeah.
Description. I just.
And they did teach shells. Which school were you at? Okay. Broomfield's always had a pretty solid math program. Yeah, that's interesting, because usually shells are left out of ABs.
Por andar con
Like my kids took BC, AB and BC, and they never got shells. We
Está
take
bien,
Calc 2 in college then.
pero
You're not getting Calc 2 credit if you didn't take
él
shells.
me está diciendo que es 0, pero ¿cómo sacarlo? Esto, sin saber ese.
All right, so the outer radius is going to be the distance to the further function. The inner radius will be the distance to the closer function from the axis that we're rotating about. So the area of a washer is going to be pi multiplied by the outer radius squared minus the inner radius squared. That's our basic geometry. Big circle minus little circle. The outer radius, everyone see which function is the outer radius? Is there any question on how you decide which one's the outer radius? Make sense? Outer radius is the one further away, so that's going to be that function up here, x plus 2. Is that good? Any issues with that? That's the one that's furthest from the axis of rotation, so that's our outer radius. And then the inner radius is just x. So that's going to be x squared. Here's something you should be thinking about. When your element is vertical, it's sliding across x's. And when it's sliding across x's, the thickness of that element you're thinking of as dx. So that tells you that you're going to integrate with respect to x. All right? If the thickness of this is dx, then in order to integrate a dx, you're integrating with respect to x. So that tells you that you can only have x's inside the integral. So when you're replacing the r0, or the r sub o and the r sub I, they should be turning into x's so that they can align with the dx and you can integrate with respect to x. And that part can get a little confusing whether you should be putting y's or x's into the integrand. And the key is that they've got to line up with that differential. If your differential is dx, then everything inside the integrand has to be turned into x's. Right? You need x's to integrate with respect to x. If you have a sleeping rectangle, if you have a horizontal rectangle, the thickness is dy. So you have a dy at the end of the integral. That means you have to turn all the things, the r sub o, the r sub I, into y's. So that gives you that's kind of like a mental check. Oh, vertical element, thickness is dx. These guys need to turn into x's. If you had a horizontal rectangle, thickness is dy. So everything would need to turn into y's to line up with that dy. Okay, so here we have a dx because this is a vertical element. It's sliding across x's. And that is the area of our washer at x. And if we simplify this, we FOIL, we get x squared plus 4x plus 4. Subtract off x squared. And our simplified area function has no x squareds, does it? Will just be 4x plus 4. That's the area of the washer at x. Then we just integrate that to get volume. It's shockingly simple conceptually that you just integrate the area and you get the volume. The mechanics of that aren't necessarily simple, but the idea boils down to something that's a pretty simple concept. All right, and then we have to get our limits of integration. They present them to us. We don't have to do any work, just 0 and 4. And then we'll do our power rule. Add 1 to the exponent, divide by the new exponent. Fundamental theorem of calculus says that this is going to be the antiderivative evaluated at 4, which is 32 plus 16, which is 48, minus the antiderivative evaluated at 0, which is 0. And so that'll give us a total volume of 48 pi. So that'll be the volume of this solid object that looks like that. Some cone-ish thing. Any piece of that you want to unpack?
You could factor the 4 out too before you.
We could. Yes, yeah, right at this stage right here, we could have factored out the 4 there or there, 100%. Yeah.
Not the same answer, but I just wanted to make sure it
Yeah.
wasn't a fluke.
No, not a fluke, not a fluke. It's one of the things we like. If you feel like factoring, you can factor. If you don't want to, you don't have to. Cool. All right. Just when you start to feel oriented, we're going to rotate by 90 degrees and integrate with respect to y instead of x. Which just feels so much more difficult, even though it's not. You know, it's just 90-degree rotation, but it does feel just a little bit more less intuitive, I guess. We're so used to thinking about, when you hear the word function, you think, passes the vertical line test. Well, it all depends on what your independent variable is. A function of x, passing the vertical line test makes it a function. But a function of y, passing the horizontal line test would make it a function. So we have to be a little bit careful. So when we look at this region down here, we have a left boundary curve. That's a function of y. And we have a right boundary curve, which is also a function of y. And we have to use a horizontal integration element, a sleeping rectangle, because you can't draw a vertical element and have a consistent upper curve and a consistent lower curve. Right? Like in the last problems, you had your upper curve and lower curve, and your rectangle always had the same upper curve, always had the same lower curve. Can't do that here, right? You draw your vertical rectangle and there's madness. But you have a consistent left and a consistent right if you draw a horizontal integration element. So we're going to think of our rectangles as stacked on top of each other, where the height of the rectangle is sideways. And the thickness of that integration element, or the thickness of your rectangle, is dy. That's the little distance, the small distance. Okay, and instead of f and g, upper is f, lower is g, when we turn it sideways, we're going to use p and q. So p is the further one, q is the closer one. That okay with everybody? So we're going to end up still with a washer. When this element rotates around the y-axis, you can see the washer that it creates. It's this direction, though, instead of this direction. But it's still a washer. And the area is still the same. When we come up with our generic formula for the area of the washer, that generic formula is still the same. It's still pi multiplied by the outer radius squared minus the inner radius squared. It's just that when we replace the r's What letters should we be replacing them with? Y's. We need y's. Because the thickness of that rectangle is dy, that means we're integrating with respect to y. That means the integrand has to be only filled with y expressions. Can't have any x's in there. Okay, so when we look at this formula, that's what it's showing. So p is going to be the distance to the outer function. So that is going to be your r sub 0. And your distance to the inner function, that is going to be r sub I. And so in this example, where p is the outer function and q is the inner function, it's going to be pi times p squared minus q squared. All with respect to y, though. So that's what that formula represents. If the q function is 0, if the q function is 0, then we just get a disk. If the q function is 0, it means that the region is touching the y-axis. So then you're going to end up with a horizontal disk instead of a washer if the region is touching the y-axis. If this curve right here was the y-axis, then you're going to get a disk. Because there'll be no space between the axis of rotation and your region. Let's try one. All right, so there is our region bounded by these three curves. Make sure you can graph the natural log function. That's a function you absolutely should be able to graph instantaneously. X-intercept is 1, 0, right? Has a vertical asymptote at x equals 0, the y-axis. That's the vertical asymptote for natural log. Okay, so this is rotating around the y-axis. If we draw a representative integration element, a sleeping rectangle, that's going to be at a generic y. And you can see that no matter where you draw that horizontal element, it's always going to be touching the y-axis. So when it rotates around, it's going to form a disk, not a washer, not a triangle, not a square. It's going to form a disk. So that tells us that our geometric object is a disk. And we know that the area of a disk is pi times the radius squared. That's our basic geometric formula for the area of any cross-section. Now when we look at our picture here of our region, there's R. R is going sideways. R is the distance of that red segment. Okay, and here we have to be super careful. We know that the thickness of it's dy. We know we need to turn that into some y expression. Okay, and here's where we have to be careful based on how the function is presented. So this function is presented as a y value. Right? Y is on the left, so it's sort of presenting as a y value. We're saying y is equal to whatever. If you're measuring horizontally, you need to present it as an x value. Right? If you have y equals something, you're measuring vertical distance from the x-axis. When you have y equals x squared, you're measuring how far away you are from the x-axis. So y equals measures vertical distance. If our element is horizontal and we want to measure sideways distance, we need to isolate x. Whatever letter is isolated tells you whether you're measuring sideways or vertically. So the way this function is presented, it's presented as measuring the distance from the x-axis up. So it's presented as measuring that vertical distance right there. Right? Really? So, right, when you have y equals natural log of x, you're plugging in the x to get a vertical distance. You're plugging in x to get y. So we don't want that. So we have to do what? We need to isolate x. So how do you convert this into an x value instead of a y value? X equals
X to the Y.
So it's going to be e to the y. So if we want to get rid of a natural log, we exponentiate both sides. We put an e down here as the base on both sides. E and natural log cancel, so we get x equals e to the y. So that'll be now the function is presented as an x value. It's measuring sideways instead of vertically. Now you say to yourself, x is dependent, y is independent. You're plugging in y's to get x's. So now your domain is over here on the y-axis. You plug in y values in between 0 and 2, and you're going to get a horizontal distance over to the function. All right, so now we are good to go. So the area is pi. This function, e to the y, that's what it's doing. It's measuring horizontal distance. So it's going to be e to the y quantity squared, which is e to the 2y. So there's the area of our horizontal disk. And volume. We integrate area to get volume. And now we're integrating with respect to y, the thickness of the element, the thickness of your cross section, however you want to think of it. Think of that dy as the thickness. And if you have a dy, gotta have y's, no x's.
Is the 0 that is in the bottom of the integral comes from y equals 0 or x equals 0?
It's coming from the y-axis. So it's coming from y equals 0. So there's our domain right there. So we're integrating from y equals 0 vertically all the way up to y equals 2. So we're imagining this stack of disks. And we're counting all those disks from y equals 0 up to y equals 2. Those disks are stacked on top of each other. Integrate. This is reverse chain rule. That's linear. Whenever you have a linear substitution, you can just integrate with the reverse chain rule. So the integral of an exponential is itself. Derivative or integral of an exponential, always itself first. And then what do we do next? Divide by 2. Once you get used to this reverse chain rule, it's quite fast. There. And then the pi over 2, I'm going to factor it to the front and just kind of focus on this exponential piece. Try to simplify it in our mind as we evaluate. All right, so we have our antiderivative piece right here. That's going to get evaluated at the 2. It's going to get evaluated at the 0, and then we're going to take the difference. That is fundamental theorem of calculus. So we're going to get e to the 4 minus e to the 0. So we get pi halves multiplied by e to the 4 minus 1. So there is, okay, rotate that. That is our answer. Don't get complacent. A lot of times we see when we have a limit of integration of 0, a lot of times we end up subtracting 0. But remember, if it's an exponential function, e to the 0 is not 0.
Remind me again, why is it that you remove the 2 and then put it into the pi over 2?
Just so that the evaluation is as simple as possible.
Okay.
So you can always factor a constant out of a derivative, out of a limit, out of an integral. And just to simplify it, you can leave it in, of course. And you know, if you wanted to write it as, you could write here, write it as pi e to the 4th over 2 minus pi e to the 0 over 2. It's just a little bit easier to get the constants out to the front, so you're just focusing on this with that. But you don't have to. There's several ways. We ready for a break? Take 10. Ready? Break. And if you have any questions, I am here.
I don't know.
So this is no. Wait, actually, this is. Oh yeah, now he's having.
If I need more volumes, sideways volumes. Oh, this looks kind of like that other one, some weird conish thing. I don't think you're ready yet to do one yet of these sideways ones, but let me do one more of these things. So again, we're dealing with a horizontal integration element. We're going around the y-axis, and so when we draw this horizontal element at a random y, that element rotates around and it's creating that washer that's this direction. So you can see that cross section there. This is what the solid object looks like. This one is truly more like a cone than that other one we did, because the inside is a cone and the outside is a cone. The other one had like a extended base, but this one has an inner cone and an outer cone. So if you knew the volume of a cone geometrically, you could actually do this one with geometric formulas. This would be the big cone minus the little cone. But we're using calculus because we can. So we know our cross section is a washer. So the first thing we need to do is find the area of a washer, which we have discovered is the multiplication of pi with r outer squared minus r inner squared. Okay. Now the catch here is that we're measuring horizontally, so we're going across here. That is going to be the outer radius. So from the axis of rotation to the further curve, the inner radius is going to be the distance from the axis of rotation to the closer curve. Now we see all of these horizontal lines, technically segments, but we always say that. So these horizontal segments, horizontal lines, anytime we're measuring horizontally, we want the equation that represents those curves to have x isolated. If we're measuring sideways, we need to have x all by itself on the left side. We need to write them as x values. We want it to measure sideways. This one, we can think of that as x equals y. Pretty easy to swap that one over. This one is going to be x equals y divided by 2. So now these two functions are measuring horizontally. This one is measuring, you plug in a y, the independent variable is on the right, dependent variable is on the left. So here you plug in y, get out x, here you plug in y, get out x. So now it's measuring sideways, measuring horizontally. All right, so now we just have to do some substitution in here. So we're going to have pi multiplied by the outer radius, that's the green curve, the green one up there. And so the green one, the function is y divided by 2. So that is the outer radius. So you're plugging in a y value and you're getting an x value. Question?
The first number is LCO.
Thank you. Thank you. Is that the outer or is that the inner? That's the inner. I saw that the green was further over to the right, so I was assuming I was writing it as the outer. The outer is this green one, but I wrote purple. I gotta change my colors here. I was trying to be color coordinated here and I screwed that up. Okay, so this one is x equals y. That's the further one. And the closer one, let's write that one right there as x equals y divided by 2. Thank you. There we go. That looks better. So the outer one is here, so that's going to be y quantity squared. Our inner is the closer one, which is y divided by 2 quantity squared. Thank you. If we would have persisted with my mistake, what do you think we would have ended up with? The negative 1 times the volume. So we could have left it how it was and put a minus sign out in front if we didn't have an eraser. If we were doing our work in pen, we could just put a multiplication by a -1. Okay, so that can be simplified a little bit. So this will be y squared minus y squared over 4. So then we can subtract off a 4th y squared from y squared and get 3/4 y squared. And if we want to group all the constants together as a coefficient, we could do it like that. So everything's in terms of y. This is good because our thickness is a dy. We're going to be integrating with respect to y. So now we know that the volume will be the integral of 3 pi divided by 4 times y squared dy. And they've given us our limits of integration. They're going to come from the y-axis because we have a dy. When you have a dy, you're looking at the y-axis. So the domain for this integral is right here. We're going 0 to 6. Oops. The constant factors out to the front. And then we do y cubed over 3. There'll be a cancellation of 3, so we'll end up with pi divided by 4 times y cubed. Evaluate from 0 to 6. And so here, again, I just sort of think about the constant being out in front. And I'm just thinking about substituting into this variable part of it. And so then we have 6 to the 3 minus 0 to the 3. 6 to the 3 is 6 times 6, which is 36, times 6, which is 216, I believe, minus 0. And 216 is divisible by 4, I believe, because that's 108 and then 54? 54, thank you. 54 pi. So there is our volume. Yeah?
Where did the 3 go and the 3 go before?
This 3 right here?
Yeah.
So when we do the integration with that, that becomes y cubed over 3. So if we left that 3 right there, then this would have a 3 under it. When we integrate the y squared, we get y cubed over 3, so then those two cancel.
Okay.
You see it?
Yes.
Yeah, good question. Those little questions, ask them so they don't nag at you as you're going through the class. All right. Let's. All right. I think you're ready to try one. You all try this one. So we've got. So with Desmos, this I built with Desmos. A lot of these, I'll just put the Desmos commands over there just so you can see it if you're playing with Desmos. Some of you probably already know how to do some of that, but that's just how you can graph some of these things in Desmos where you want to restrict and you don't want the graph to go on forever or whatever. You can put these restrictions in brackets or whatever those things are called. What are they called? Braces. Braces. So it looks like a kind of like a, I don't know what that shape is. It's like the toilet bowl at Waterworld, except that there's no hole in the bottom. Those fun rides, we spun around in circles and spit out. All right, oh, I should take roll. That's part of my job. Other duties as assigned. Fatima. Arnulfo, Nikesh, Nolan, Jack, Jordan, Danny, Chewy, Brianna, Evan,
70.
Lauren. Yesenia. Okay, she was emailing me earlier. Trevin. Gilbert. Kishore. There you are. Brian. Ravel. Peyton. Dalila. Ben. Alvaro. Jose. Ishmael. Yes. Reza. Laura. Sebastian. Erica. What's the volume? How much? Pi over 5? Somebody else get pi over 5? Did you ask Siri?
No.
She's very good at math. All right, so let's go through. Stop me if you feel like something is not making sense. So it's sideways, so I'm thinking of our outer is going all the way over to the 4. The right curve is the vertical line, y equals 4, x equals 4. The left curve is this square root function. And so remember that x to any fractional power is always going to sort of have that bird wing shape to it. And we always look at our geometric shape first and find the area of that geometric shape. This geometric shape is a washer. So we know that we're going to do pi times the outer radius squared minus the inner radius squared. And the outer radius is 4. So we're just going to have 4 squared in there for the outer radius squared, 16. And the inner radius is the square root function. Now notice that the right-hand curve was already presented as an x value. The left-hand curve is not presented as an x value. Right? It's presented as a y value. Let's see, I'm using red. Let's get my colors straight this time. So y equals square root of x. If I want it to be measuring sideways from the y-axis, that needs to be rewritten. We need to reconceptualize it, not measuring vertically, but measuring horizontally, so we isolate the x. So that tells us that x will be
Y squared.
y squared, exactly. So now it's measuring horizontally. Now you plug in a y and you get out an x, you get out a horizontal distance. So that's what's going to drop in over here. So we're going to have y squared quantity squared. So if we simplify our area function a little bit, we get that. So there is our area function. That's the area of the washer at a random y value. So the volume will be the integral. Pull the pi to the front. Looks like we're going from 0 up to 2. So this is our domain over here on the y-axis. We have washers for all of the y values between 0 and 2. One of them is really a degenerate washer. When you plug in y equals 0, you actually get a disk. There's not going to be a hole in that one washer. Everyone see that? As soon as you are off the origin, then you truly have a washer and there's a hole in the middle. But this one at the bottom, when y is 0, is going to rotate around and actually create a disk of radius 4. So there's no hole in that one. But we still say it's washers. All right, so integral 0 up to 2. We have washers for all these y values, 0 up to 2. And then we just integrate our function here. So 16 minus y to the 4th dy. So So we'll have 16y minus y to the 5th divided by 5 from 0 to 2. So we'll do the upper limit of integration. So we're going to plug a 2 in there, and that to me looks like 32 minus 32 fifths. And then we plug in the lower limit of integration and get 0. All right, so I'm going to factor 32 out of there and get 32 pi multiplied by 1 minus the 5th, because I can do that in my head really easily. 1 minus the 5th is 4 fifths. So we're going to have 32 pi times 4 fifths. So that's going to be 128 pi divided by 5. Wait, what was your answer, Ben? Did you do that, Pete? Did you rewrite that?
Yeah.
It's done 32 minus 32.
Say that again.
Might have just done 32 minus 32, and then it was pi over 5.
Oh, yeah. You could have made a arithmetic mistake right there, possibly. Yeah. Try to figure out your arithmetic thing. All right. Random. That sounds like a scary word in math. Random. Well, when you rotate around the x or the y axis, that's a little easier to deal with than rotating around a random vertical or horizontal line. And by random here, we are going to stick to vertical or horizontal. In Calc 3, you need vectors if you want to be able to rotate like around a random line, truly random. So it's not vertical or horizontal. All right, so let's try to wrap our head around this. We conceptually already know what's happening. If we're dealing with a disk or a washer, we have to figure out for a washer the furthest curve, the closest curve, or for a disk, the radius. And we have to remember two basic facts. If we want a vertical distance, it's going to be upper minus lower. If we want a horizontal distance, it's right minus left. That basic geometry is going to be our friend. So let's take a look at this. So graph of 1 minus root x. Y equals 1 is this horizontal line. X equals 1 is this vertical line. But then they tell us, hey, let's rotate around y equals 1. That's going to be our axis of rotation. So this region is going to spin around that axis. And what are the cross sections going to be? We're going to end up with disks. Right? If we take a region that's touching your axis of rotation, whether it's this way or this way, if it's touching it and it rotates around, it's going to create a disk no matter what, if that region is touching the axis of rotation there. So when it spins around, now we're used to spinning around a horizontal axis down, but we're sort of spinning up here. But it's still the same thing. So let's draw a representative element. All right, so there is a random vertical element at x, but this thing is rotating up. This still dictates the radius of the corresponding disk at x. So at x, there's the radius. All right, so our shapes, we know our shapes. Our shapes are disks. And we know that the area of a disk is pi times the radius squared. Are we going to be integrating with respect to x or with respect to y? We are going to integrate with respect to x because we have a vertical element. The thickness is dx, so we know that we're going to have a dx in the integral. So that means everything's going to be x's. All right. This vertical element, we're measuring vertical distance. Vertical distance is upper minus lower. A lot of times when we're doing the disks around the x-axis, oh, the function, that's the radius. The function, that's the radius. The function is not the radius here. Right, the radius is this distance, which is upper minus lower. This is a vertical distance right here. It's got to be positive. So that radius is going to be what? Upper function 1 minus the lower function 1 minus root x. That will be our radius. So upper function, so vertical distance, we have to do the upper function, oops, the upper function right there minus the lower function. Right, that's a vertical distance. Take the upper y value, oh, the upper y value is 1. Minus the lower y value, oh, lower y value is 1 minus root x. So 1 minus all that in parentheses because we'll have to do a distribution. So that is the radius right there. So the radius is that. Upper y coordinate minus the lower y coordinates. Lower y coordinate. So the simplification here is pi multiplied by, distribute the minus 1 is 0. We get root x squared. Oh gosh. That simplifies pretty nicely actually. So that is the area of the disk. Let's check our extremities because this feels weird. It's definitely different. Over here at x equals 0, what should the area of the disk be? When you're at this single point rotating around the axis that it's on,
0.
you get 0 area, right? That thing is not, it's creating a degenerate disk. It's creating just a point. And then this one's getting bigger disk. Bigger disk. The biggest disk is over here when x is 1. That's creating a circle of radius 1. And the area of a circle of radius 1 is pi r squared, where r is 1, so that's pi. If we plug in 1 right there, yeah, we get pi. So this is looking like the legitimate area function. All right, the integral and solving of that's simple. Let's make sure we understand this part. Looking at that, does everybody understand that that is what r will be? So the first thing you say to yourself, are you measuring vertical or are you measuring horizontal? If you're measuring vertical, you need to be subtracting y coordinates. If your function isn't presented as y values, you have to make sure you have y isolated, and then you subtract them. Horizontal, isolate x, and do right minus left. All right. So the volume piece is the integral of this function with respect to x. Vertical rectangle thickness is dx. Limits of integration, we are going sideways now. The limits of integration are coming from down here. Even though it's 0 to 1 y, in your mind, you better be thinking that this is the 0 to 1 right down here. Because the vertical elements are all coming from this interval 0 to 1 on the x-axis. So then this is going to be pi x squared divided by 2, 0 to 1. So we're going to have pi over 2 times 1 minus 0. There's our volume. All right, so the real difference is that this radial value, this radius here, you have two curves that are generating the endpoints for that radius. But you still haven't done anything drastically different. You're still doing upper minus lower for a vertical distance. All right, let's try another one of these. So here, our axis of rotation is the line x equals 4. So this is where we're rotating around. Okay. So we're rotating this way. Do you see that if you're going to use a washer, you have to use a horizontal element? Right? If this element, horizontal, is going to rotate around that, that's what's going to create a washer. If you said, hey man, I want to try to use a vertical element, so you drew that, what shape will you get when your element is parallel to your axis of rotation? You're going to get a cylinder, right? If you take this and you swing it all the way around that, you're not going to get a disc or a washer, you're going to get a cylinder. Does everybody see that? So if your axis of rotation and your element are perpendicular, you get a washer if there's a gap, but if there's no gap, you get a disc. But if it happens to be parallel, which is what we're going to do next, you're going to get a cylinder, which in Calc 2 we call a shell, a cylindrical shell. Okay, so we don't want a shell yet. We want to deal with what we know. To create that washer, we have a horizontal element, horizontal integration element, sleeping rectangle. That's going to be at a random y. And we know that the area of a washer is pi times the outer radius squared minus the inner radius squared. Okay, so if we look at the curve that's furthest from the axis of rotation, that'll be the outer radius. The curve that's closest will generate the inner radius. The axis of rotation is way over here. The curve furthest away from it is this green dotted line that I've drawn there. The curve that's closest to it is the red dotted line. Okay. All right. So we are finding horizontal distances. That means we're subtracting x values. So our functions have to be presented as x values. In other words, we have to isolate x on the left side for each of them. So let's look at the outer radius first. This function over here, so we're trying to find the distance between this purple dot and that purple dot. That distance right there, that's horizontal. So this over here has to be written as an x value. Oh, it already is. X equals 4. It's written as an x coordinate. Come over here. What about this one? What is this outer curve? What's its equation?
X equals 0.
X equals 0, so it's already written as an x value. So our outer is 4. And you see, no matter where you draw your element, that left curve is over here at x equals 0. The right curve is at x equals 4. That distance is always 4. It's constant. So our outer is a constant. So we are going to be at this stage. Oh, we already had a 4 squared earlier. All right. Now our inner. So when we go to our inner, we're here and here. Okay, this one's the same thing, x equals 4. That distance, that x coordinate right there is x equals 4. That hasn't changed. Now over here, this curve, the way it's given to us, the way it's presented, is presented as a y value, not an x value. It's presented as y equals square root of x. But if we're measuring horizontal, we want to reconceptualize this equation. We want it to measure sideways. So that means we need to isolate x, so we're going to get x equals y to the 2, y squared. That's the left curve. So horizontal distance for this red line here. Subtract x coordinates. The x coordinate here is 4. The x coordinate here is y squared. So we're going to have 4 minus y squared, quantity squared. So there is our formula for the area of the washer. Let's go ahead and simplify this mess. So in here, we're going to FOIL this out. And when we FOIL this out, we'll end up with that. And then when we distribute the negative sign and collect like terms, I see a cancellation of the 16s, and I see an 8y squared minus y to the 4th. So that is our simplified area of a washer. And then for the volume, we're going to integrate 0 to 2. Integrate area to get volume. Pi can come to the front. 8y cubed over 3 minus y to the 5th over 5, 0 to 2. Plugging in 0 gives 0, so, yeah, question?
Why are our limits 0 to 2?
So if we look up here, the region, we're integrating with respect to y because we have a sideways rectangle, so its thickness is dy right there, which tells us that we're integrating with respect to y coordinates, and the y coordinates go from 0 to 2. Does that make sense? So the interval that you're integrating on is always perpendicular to your element. So that element right there, that red element, is sliding between 0 and 2 on the y-axis. We plug in our upper and lower limit here, upper and lower endpoints. Plug in 2 and we're going to get 64 thirds minus 32 fifths. And then subtract off 0. Plugging in 0 gives 0. So we just have to simplify that. We're going to get pi times something over 15. That thing needs to be multiplied by 5, so it's 320, I think. That thing needs to be multiplied by 3, which is 96. So it's pi multiplied by something over 15. 320 minus 100 is 220, plus 4 is 224. And that's written weird, so we would normally write that as 224 pi divided by 15. Any step there that you want clarification on?
Yes.
Yes.
Could you go over the outer R, y?
The green one?
Yes, the minus, the 4 minus y squared.
Oh, the inner one here, this one?
Yeah.
So that red one, we're trying to measure this distance right across here. So that distance right there, that's the distance we want. This is horizontal, so we want to take the right x-coordinate and subtract off the left x-coordinate. The function was originally written as a y-coordinate, though. So we want to square both sides and isolate x to the left so that it's now measuring horizontal distance. So now x equals y squared is going to measure from the y-axis over to here. We only want this distance, so we're going to do the right x, which is 4, minus the left x, which is y squared. Bless you. So that part right there is right minus left for that red piece there.
So the reason why we are doing this is that because our axis has changed. It's not 0 anymore.
It's been shifted. And so we still are going to use the same principles, that the inner radius is going to be from the axis over to the closer curve. And then that creates this horizontal distance. Anytime we want a horizontal distance, we have to do right minus left. If we did left minus right, we get a negative number. So we have to do right minus left. So 4, and it's kind of one of those things, like if this whole distance right here is 4, and this distance right there is y squared, then this distance right here is 4 minus y squared. That's kind of the idea there. So when we say that x is y squared, that's measuring this distance right there. X equals y squared measures distance from the y-axis over, just like y equals x squared measures from the x-axis up. And so we want the complement of this. So if we want just that distance, we want the complement of that, which is this. So we do the total minus this, which will give us that.
Thank you.
Yeah, it takes a little practice to sort of visualize exactly why it is what it is. So let's take a look at our last slide, the dreaded torus, or donut, if you prefer. We want to find the volume of that thing. The volume of this torus. So the torus is generated by taking a disk and rotating it around an axis. This torus is generated by this disk down here. So that disk right there has a center of 3, 0, and its radius is 2. So I've done a couple of things there. Here is the equation of the circle of radius 2 centered at 3, 0. So that's the equation of the generating region. And there's the graph of it. We have to use a horizontal element to create a washer. If we used a vertical element, again, we would get cylinders, which we're not doing yet. So that horizontal element right there is going to create a washer when it rotates around the y-axis. So this element right there, between those two dots, when it rotates around the y-axis, it's going to create a washer. So let's set this thing up. So we know that the area of a washer is pi times r outer squared minus r inner squared. The outer distance, so the axis of rotation is over here. The outer is this green segment. This is the distance to the further curve, right there. And then the red dotted line is measuring the inner radius, which is that distance right there. So there is r inner, and there is r outer. So, horizontal measuring is a difference in x coordinates. So that means any curve needs to be written as x equals. So I took the equation of the circle and solved for x. When you solve for x, you get that the right side is 3 plus the square root, and you get that the left side is 3 minus the square root. You isolate x from that equation. So the area then of our washer, we're going to do r outer squared. Ooh, that's this one, right? The long one. That's our outer right there. The left is 0, so that's at least easy. So it's 3 plus the square root of 4 minus y squared, quantity squared, minus our inner, which is the orange one down here, so 3 minus the square root of 4 minus y squared, quantity squared, close parentheses. That is the area of the washer. Yeah?
And this is taking into account the shift and all that, or that's something we don't have to worry about?
Well, the equation of the circle is taking into consideration where this circle is. So it is, the center of this circle is at 3, 0, and the radius is 2. So this takes care of all of that. And this will simplify. Don't want to go through that right now. So I want you on your own before Thursday to try to simplify that, because one thing I've noticed in Calc 2, there's a lot of bad algebra in Calc 2. So see if you can simplify this. This just needs to be FOILed. You should be able to do it. Yeah.
Just a quick question.
Sure.
Again, I think you already said this.
That's
but
okay.
Why wouldn't you inverse the y? Find x.
You mean use a vertical?
Yeah. Use.
So the axis of rotation is vertical. Here is our axis of rotation, right there. So if we take a disk and we rotate it around that axis, it's going to create the donut. And if we chose to use a vertical element around a parallel axis, it's going to create a cylinder and not a washer, which we will learn to do in 2 minutes. But at this stage, we only know how to do washers and disks. So we have to choose a horizontal element to go around. We have to choose a horizontal element to go around if we're going to create a washer.
Okay.
Does that make sense to everyone? If your axis is vertical, your element needs to be perpendicular to it to create a washer or a disk if it's touching. If your element and your axis are parallel, when it rotates around, it creates a cylinder. We haven't done the geometry of a cylinder yet. We've done geometry of, washers and disks and squares and triangles, but not a cylinder. So we'll get to that. So before Thursday, see if you can simplify this and then you just integrate it to get the volume. And you can use some symmetry. We certainly see that the symmetry here is pretty obvious. Why are you grabbing the page? You're so aggressive. So that, I don't quite know why. So the upper half of the torus is created from 0 to 2. So you could go 0 to 2 and then double it to get the full torus. So try to do that algebra before Thursday, because you want to make sure your algebra is sharp. Make sure you can do these types of things. All right, let's go to, everyone's anxious to look at shells. Well, let's take a look at shells, aka cylinders. There's a lot of shapes that you can't, there's a lot of shapes, a lot of regions that get rotated where you can't create a disk or a washer. For example, when we look at this shape right here and it's going to be rotated around the y-axis, we can't use a horizontal element easily because the right-hand curve is changing depending on where you draw the element. But if you draw a vertical element right here, then it has a consistent upper curve and it has a consistent lower curve. So that's the desired direction to draw your element because you've got a unique upper and a unique lower. There's not some weird transition. But we just saw that when you have an element parallel to your axis, the shape that it creates is a cylinder, not a washer or a disk. So if we want to stick with this model, then we have to figure out how to use shells. So here is our generating rectangle. It gets rotated around and it's going to create this shell. So instead of thinking of stacking disks or stacking washers, the idea for filling out the volume here is more like you're thinking about nested cylinders. So you're just imagining all these cylinders. They're not stacked on top of each other, but they're inside of each other. So you're creating all of these cylinders that are going to fill out the volume. And we do the same thing that we did with the washers and the disks. If we come up with the equation for the area of a cylinder, which is 2 pi r, that's the circumference of the base, 2 pi r, multiplied by the height, that gives us the area of a cylinder. So 2 pi r right there, so 2 pi r, and then this is the height, and then that's the thickness. So circumference, and then height, and then thickness. So this is how we're going to create these cylinders. The circumference of the base times the height is the area of the area of the cylinder, and then if you multiply by dx, that creates a cylinder with thickness. It turns it from what we were calling a cross section into a slice. It's got some volume. So let's try one of these thingies, and we'll see. Oh, here's just a picture of as those cylinders get narrower or less and less thick. As the width gets thinner and thinner, you can see that it's conceptually plausible that the cylinders fill out the volume, and then if you add up all the little volumes, the volume for each cylinder, then you should get to the volume of the thing, of the object. And you do, and it's just the limit of a Riemann sum. Limit of a Riemann sum is a definite integral, and if there's a hole in the cylinder, you are going to, or not a hole in the cylinder, if there's a hole in the region, you don't have to worry about it like you did with the washer so much, right? Because now if that hole is there, the cylinders are just going around that hole in the middle of it. So you don't have to do that subtraction like we did for the washer. But there are times where your cylinder height might be between two curves. It might not just be the x-axis or the y-axis, so it might be an f minus g or a p minus q. We'll see different scenarios of that. So let's try one, and I'll point out all of the pieces to this. All right, so let's look at this. Our axis of rotation is the y-axis. So we've got this vertical axis right there. That's where we're rotating around. If you drew a horizontal element, you would get disks. We're going to go with shells, though, so we're drawing a vertical element. So this vertical element right here at a random x. And we're going around the y-axis. So that element, when it rotates around a parallel axis, it creates a cylinder. And that's what this is showing down here. If we take that element and rotate it around, that's what the red thing is down there. Right? So that's the cylinder, the corresponding cylinder. So, area of a cylinder. The cylinder is 2 pi r times the height. So that's our new formula. Generic cylinder. Circumference of the base is 2 pi r, and then you multiply by the height to get the area of the cylinder. What letter are we integrating with respect to, x or y? X. We have a vertical element, its thickness is dx. So we're integrating with respect to x. So that's how we know whether we're doing a dx or a dy. Horizontal element, dy, vertical element, dx. So that tells us that the r and the h need to turn into x's. If we're integrating with respect to x, the r and the h need to turn into x's. So the hard thing about the cylinder is that we're going to have things in two directions. All right? This is the radius right here. That looks all choppy. Let's go red. That is the radius. This is the height. Right? Those are in two different directions. The washer, we had our inner and our outer, they're in the same direction. So we have to be a little careful here. We know the r and the h need to be turned into x's. So we have 2 pi. When you look at that radius, can you see what that radius is in terms of x? If this x value right there was 1, what would the radius be? 1. If that x value was at a half, what would the radius be? A half. If that number right there is x, what's the radius?
X.
X. Right? X is actually measuring the distance to the y-axis, which is what the radius is. That's the radius. The radius is just x. If you look at that purple element right there, the distance it is from the x-axis is whatever the coordinate is at the base of it. Right? If you're at 2, you're 2 units from the x-axis, that's your radius. If you're at a half, you're half a unit from the y-axis, so that's your radius. If you're at x, you're x units from the axis of rotation. So r is just x. How about the height? Yeah, the function, right? The function is going to be the height, 1 over 1 plus x squared, yeah. We have that. I'm going to write this in a strategic way. I'll explain in one moment. I'm going to write it like that. That's the area of our cylinder. What do you notice about the numerator's connection to the denominator there?
Inverse. No.
Derivative, right? The derivative of the denominator is the numerator. There is a function that has that property. If you integrate natural log, if you integrate, and your Calc 1 teacher did not point this out to you, isn't that the relationship with 1 and x? The derivative of x is 1. So watch what happens here. And we're going to have a shortcut for this type of integral at some point. So the volume is going to be pi integral 2x over 1 plus x squared. And we're integrating with respect to x. The x's go from 0 to 2. At some point, I'll refer to this as log form. Log form is when the derivative of the bottom is the top. And we will see that this turns into natural log absolute value of the bottom. We'll get there, but we'll call that log form at some point. So at this stage, the only integration technique you have is substitution. We've seen a couple of shortcuts for substitution, but that's really the only integration technique you have. And the way you would do this with substitution is to let u be 1 plus x squared, and then du is going to be 2x dx. So this integral can be rewritten as the integral of, let's see, oh, isn't that just du over u? 1 plus x squared turns into u. 1 plus x squared is u. And then 2x dx, that's du. And now we have to go, limits of integration are going to change. I'm going to put some placeholders in here instead of figuring out what they are in terms of u. You could use this and plug in u equals 0, plug in u equals 2, or excuse me, x equals 0 and x equals 2. You can do that. I don't want to focus on that right now. Let's just put placeholders. The most important thing I want you to see is that this is natural log of absolute value of u on those placeholder limits. Right, the integral of 1 over u is natural log of absolute u. And then if we go back to the original, so this is natural log of 1 plus x squared on the inside. And then our original limits are 0 and 2. So this is the piece I want you to see. Isn't this what you did right here? If the denominator's derivative is the numerator, the answer is natural log of the absolute value of the denominator. Isn't that what we ended up with? Right? The denominator's derivative is the numerator. We end up with the natural log of the absolute value of the denominator. So that's going to be something we're going to see it so many times this semester that we're going to call it log form because it's going to show up so much. We want to have a name for it. So now let's plug in the 2. We're going to get natural log of 5. Don't need an absolute value. 5 is positive. What do we get when we plug in 0?
1. Natural log of 1.
We get natural log of 1, and natural log of 1 is? Natural log of 1 is? 0. So we end up with pi times natural log of 5. That'll be our answer. Yeah?
Wouldn't you be finding the new numbers on the integral?
You don't have to. You can always go back to the original. If you back substitute and get rid of the u and go back to x, you can use the x limits.
Gotcha.
And I didn't want, you can put in u limits here, for sure. Plug in 0 and get 1, plug in 2 and get 5. But I wanted you to see that our antiderivative is really just the natural log of the absolute denominator.
Gotcha.
That's the important thing, is to notice that, oh, if you have this scenario, log form, you always end up with natural log of the absolute value of the denominator. And so it gives us a shortcut.
Okay.
Let's try another one. All right, so here's a region. You definitely don't want to draw, you could use vertical elements here and break it into 2 pieces and use disks in 2 different places. It's going to be easier though if we draw a horizontal element at a random y. We have a consistent right curve and a consistent left curve. We don't have to do any subdivision of r like we would if we did a vertical element. So when we're rotating around this x-axis here, we're rotating around that, the element is sideways, the axis of rotation is sideways, so when that rotates, you're creating a cylinder. All right, we know the area of a cylinder. The area of a cylinder is the area given by 2 pi rh. 2 pi r, circumference of the circle, circumference of the base, multiplied by the height. That'll give us the area of the cylinder. Are we integrating with respect to x or y?
X.
Y.
Good. If it's not x, it's got to be y. Why are we integrating with respect to y?
Because it's horizontal.
Because it's horizontal. What's the thickness of a horizontal element?
dy.
dy. Thickness of a vertical is dx, so you're integrating with respect to x. Thickness of a horizontal is dy, which means integrate with respect to y. That makes sense, Sebastian?
Yeah.
So what letter do the r and the h have to turn into?
Y.
They have to turn into y's, because we're integrating with respect to y's. They have to turn into y's. Okay. So, let's take a look at this. The radius, and this is again the tricky part, is that the radius and the height are in different directions. All right, the height is horizontal now, and horizontal distances are differences of x coordinates. So that red distance right there, we want to do the right x and subtract off the left x, but we look at those equations and they're not written as x coordinates. They're written as y coordinates. They're measuring vertical and not horizontal, so we have to change them both. So we're going to make this one x equals, we add x and subtract y. Now the right one is measuring horizontal. And this one, we've seen this one a couple times, x equals y squared. That's going to be the left one. How about the radius?
Y.
Do you see that it's just y? If you, wherever you draw this horizontal element, y is the distance it is from the axis of rotation, so y is the radius. So this is going to be 2 pi y, and then the height is this horizontal distance, which is right x coordinate, 2 minus y, minus the left x coordinate, which is y squared. So there is the area of our cylinder. So we could write this as 2 pi times, I'm going to write it in descending order, just because of my math brain. Should be written in descending order. Until we get to power series, until we get to infinite series. Then we're going to switch our perspective and we're going to write it in increasing order. All right. So that is our area function. And our volume will be the integral from, we're integrating with respect to y.
1.
Everyone agree? 0 to 1? So we're integrating with respect to y. Your element is always perpendicular to the domain. So we're thinking about cylinders being formed for all of these y coordinates between 0 and 1. So those are our limits of integration. And then we integrate this polynomial. And integrating that polynomial is it's not as crazy as it seems. We like integrating polynomials. Easier than integrating log functions. Do you know how to integrate a log function? All right. Plugging in 0. Is it going to give us anything? Nope. Nah. So we just have to plug in the 1, subtracting out 0. Of course, we can ignore. So we plug in a 1, we get minus 1/4 minus 1/3 plus 1. Now we just have to do some arithmetic here. We know that the common denominator is 12. So this one needs to be multiplied by 3, this one needs to be multiplied by 4, that one needs to be multiplied by 12. So what do we end up with? 5 in the numerator. And then a 2 out front can cancel into that 12 and give us 6. All right, anyone have a question on that one? So we are in, what is it, 6-3? No, 6-4. This is 6-4. So we finished 6-3, so you should be able to do all your homework through 6-3 by Thursday. Should be able to. Maybe you don't finish it by Thursday because Tuesday to Thursday is so fast. But you can do all those now. And you don't want to get too far behind on the homework, so you should be churning away at the 6-2 and 6-3 homework between now and Thursday. All right. Good luck out there doing math. How you feeling?
What about this?
You have something, some virus?
I have a cold. I keep getting like sick. I was sick 2 weeks ago.
Oh no! Doesn't it suck? It's such a drag.
That's not even the quest out.
My wife and I both got sick coming off a plane this summer. We were sick on our backs for 2 solid weeks, and then we were still walking and coughing for another week. Like, really? Such a nightmare. No fun. Well, whoa, there's a fish in your bag. That's not a bag, I guess. What the heck is that? What kind of fish is it? It's a trout.
I don't think it's a true. It looks like a, I think it's a duck.
I don't think so.
Oh, that's so funny. Let me know if anyone has a question. I will stick around.
I have a question.
Sure.
But it's not about the work we did.
That's okay.
It's about one now.